All right, today we're doing kth smallest element in a BST. This is Leetcode 230. It's a medium problem, and the problem goes as follows. Given the root of a binary search tree and an integer k, return the kth smallest value, one indexed of all the values in the nodes in the tree. And you'll see that one indexed is here as well as binary search tree. Now, one fact that you just kind of need to know is that the in order traversal of a binary search tree will give you the elements in the tree sorted in order. That makes sense. And let's go ahead and review what in order traversal is. So first, for any given node, we're going to go to the left if that's possible. Then if we've already either visited everything on the left or there is nothing to the left, we process the middle. So that node, right? For example, if we're at 3, we would maybe like print the current node, for example, right? Whatever we want to do, we do it. And then we go to the right. And it's also important to note that these are all forms of depth first search. So there's pre, post, but in order is also depth first search. So that means that we're going to go as deep as possible before going back. All right, let's do it on this example here. I'm just going to draw on the example. But here, we're going to start at our root node. What are we going to do first? We're going to try and go to the left because there is a left, right? So now we're going to go to the left. And then can we go anywhere anymore? No, we cannot. So we cannot go to the left. Our step 1 is done for this node. What are we now at? We are at the middle. So middle, we can print our current node or add it to our traversal. So I'm just going to call this array or this list result. So 1 will be the first thing that we add to our result. Now that we're still at 1 and we're at step 3, we have to go to the right, right? So we go to the right and now we're here. 2 obviously is a leaf node, so it doesn't have a left. It does have a middle. So what do we do with the middle? We add it to our result, and it doesn't have a right, right? If we go to right, there's nothing. So we are done with 2. That means we go back up to 1. 1, we were done with 3, so we're done with 1. Now we go back up to 3. 3, we're done with the left, so we're now in step 2. Step 2, we have the middle, and now we're done with node 3. We go to the right. And what's at the right? Well, there's nothing to the left. There's nothing to the middle. There's nothing to the right. So we get 1, 2, 3, and 4. And you can see this is a sorted array of all the elements that were in this tree. And that's just due to the way BST works, right? So I think it's pretty simple to understand if you don't already how to do a in order traversal when you're looking at it. It's a little bit harder to actually translate that into code. Now, with the recursive method, you can basically just go ahead and abstract everything away so that you're only really thinking about these 3 steps. And what's essential to realize is because the answer is given basically by doing depth first search on this tree, this whole question is just to test whether you can do depth first search. So we're going to code depth first search using the recursive method, which, like I said, is very intuitive as long as you remember what the traversal is or what the 3 steps of the traversal are. And we're going to do it really quickly here. So let's go back to our code. Let's go ahead and write the recursive solution. So let's not even think about it right now. Let's just think about getting DFS working. Now, you could do it just by using this function, but I'm going to make it even simpler and just make a helper function that does exactly what we just did in our demonstration. So we'll have the root and we'll also have the traversal here. So the traversal will keep track of all the nodes we've been to. And at the end, we want our traversal to look like this, right? We want it to have all the elements that we've been to in the correct order of our traversal. Now, with the recursive method of depth first search, it's really easy, and I'll show you why. First, we're going to see if our root is none, or if not root, right? If our root is nothing, then we don't need anything. We don't need, our traversal is empty, right? So we just return. But if we have an actual node there at our root, we have to traverse it. So first things first, we're going to go to the left. So we're going to return, and we actually don't even need to check if there's a left, because again, if there is no left, it's just going to return, right? Now, what if once we're done with that, what do we do next after we're done on the left? We process the current node. So that we process the current node and cross it out, right? We're done with this node after we do this. So let's go ahead and add the current value to the traversal once we've reached our middle node, or if we've reached our middle step. And now we're done with that node. We're done with that node. So we need to go back and see if there is anything to the right. So now what is the next step? What is step 3? Well, we have to go to the right, right? So here we're going to go to the right, and we are actually done with our depth first search. We don't have to return anything here. We can just have it be a void function, I guess, because our traversal has everything we need. We have the order of the elements of this tree. So how am I going to do this here with Kate smallest? Well, it's easy. I'm going to go ahead and do my little DFS. And I'm going to pass in an empty array as that traversal. I'm going to call that array result. So, excuse me, I don't need K here. So now that we have result's going to have basically our answer. We just need to get the correct element. Now, what element is that? Well, you can see that K is 1 indexed. So that means the first smallest value would be the 0th smallest value or would be the 0th index of our array. So we need to make sure we're getting K minus 1 because arrays are 0 indexed in Python, right? And that will be the answer for our question. Let's go ahead and run this. Let's see it's accepted. And let's go ahead and submit. And you can see this works. So whenever you're trying to do depth first search, it's much easier to do the recursive approach. But sometimes you want to do the iterative approach, and this is a good opportunity because it's a very simple problem. It's basically just asking you to code DFS to also practice our iterative approach for when the iterative approach is a little bit easier to code. It may not be this problem, but there are definitely other problems where it is easier to use or it is more convenient to use the iterative approach. So for our iterative traversal of this tree, we should really consider what the best way to code this should be. And it's not as obvious as the recursive solution where we can just abstract a lot of it away. We really need to think of what symbolically everything we're doing means so that when we code it up, it makes sense. All right, first things first, no matter what, we're going to have a current pointer that is going to be pointing to the root node at the beginning. So I'm going to go ahead and use red for my current pointer. And we also need to keep track of 2 things. First of all, we're going to have a stack. Now, this stack is going to keep track of the node we need to go back to, the nodes we've been, right? And the node we need to go back to once we reach a dead end in this tree. So stack is going to be a list or an array. And then next, we're going to also have our result. So this result will be the traversal that we make. So we know that our result should be 1, 2, 3, and 4, but how do we get that result? Okay, starting over for this traversal, we are going to have a current pointer that points at the root node. Now, to keep track of this node that we've been to, we need to put it in our stack. So we're going to put 3 in our stack. Okay, now that it's in our stack, we need to look at step 1. What is step 1? Well, if there's a left node, we need to forget everything we're doing and go to the left node before we continue on. So we're going to move our pointer to the left node, which is 1. Okay, 1 we're going to add to the stack. Now, so step 1 is done. There's nothing on the left. So we need to do step 2, which is process what's in the middle. In this case, there's a 1 and we need to add it to our traversal. So we're going to go ahead and do that. 1 is the first node that we have visited and are done with. Remember that. We're done with 1 now. We won't be going back to 1 now. So now that we're done with 1, what do? Well, we represent that by getting rid of 1 in our stack. So now our stack just has 3, and we can go to step 3 and finally finish this node off. We're going to go to the right. Okay, so the right is 2. Now our pointer is pointing at 2. Go ahead and add that to our stack. So 2 doesn't have a left. It does have a middle. So we go ahead and process that. We add 2 to our result. And we know we're not going to need to come back to 2 either because we've already done step 2. So we're done with 2. There's no right either. So like I said, we're done with 2. This is the situation in which our stack actually becomes useful. We actually have to look at it because which node should we go next after 2? Well, it's not 1, it's not 2, and there's only one other node we've been to, and that's 3. And because we preemptively deleted the node from our stack when we were done visiting it, when we were done with it, we know now that the only node that we haven't finished our work for, or we haven't done step 2 for, is the node at the root. So our pointer goes once again all the way to the root. So our pointer is now pointing at the root, 3. And what do? Well, we've already finished step 1, remember? And so we can go ahead and do step 2, which is to add our 3 to our results. And we can go ahead and also now cross it out of the stack because we are done with 3. There's nothing more we need to do with 3. Now we can finally go to the right. And at the right, so you can see our current pointer is now pointing to the last node, 4, that we haven't been to. Go ahead and add that to the stack. See that there's no left, so we go ahead and process it by adding it to our traversal. We add it to our traversal. Let me cross this out just to be clear. It's already been done, 3. So yeah, we are done with this in our traversal. We add it to 4. And then we see if there's a right. There is no left or right child of 4, so we are done, and now we were done with the algorithm. But you see, it's important that we pop the stack at step 2. And if you think of it this way, it's a very easy if-else statement in order to write the logic for this binary search tree DFS. So let's go ahead and code that really quickly. So this is our DFS solution. Let's just go ahead and reset it, and we're going to go back and look at the problem description. Now, since we're doing the iterative way, we no longer need to have that helper function. So let's go ahead and just make a current pointer pointing to the root, just like we said in our example. And we're also going to make a stack that's now empty and a result. This is going to be the traversal. Okay. Now that we have these 3, we can go ahead and start iterating or start traversing our tree. So some people write while true. There are a lot of ways to code this up, and I'm going to try and teach you the most simple way, the most intuitive way that we showed in the logic of the diagram that we made earlier. It's kind of hard to remember every single way. There are a lot of ways to do it, but this, I believe, is the most intuitive one. And if you just remember the logic, you won't have to memorize any code. If you remember the logic, you'll be good. Okay? So when should we end our traversal? Well, we should end our traversal when we're sure there's no more work to do. In other words, cur is none because it's pointing to some dead end, and also the stack has been finished, so there are no more nodes for us to go back to. Okay, so while cur or stack, while cur is not yet pointing to a dead end, and it does not have anywhere to go back to in the stack, we can continue our traversal. So first things first, what did we do? Well, we added cur to the stack, right? So let's go ahead and do that real quick. Okay, now cur is in our stack. So for an example, 3 would now be in our stack. What do we do next? Well, we can go ahead and start going to the left. Remember, that's the first thing that we try. So if cur dot left, we're going to set cur equals the cur.left, and we are good here, right? We're good. We went to the left. If there is no cur.left, what do we do? Well, first we pop from the stack, right? Cur is now our popped item from the back of the stack. Remember, what is this circumstance, right? This circumstance is when we were at the node 1, right? There's no more possibility of getting to the left, okay? So what can we do? Well, that means we're done. We can get rid of 1. We're done with 1. We just need to add it to our result, so process it, and we pop it from the stack because there's no way we'll have to go back to 1. We've already finished everything that we need to do for 1, right? So now what do we do in this case? Well, what was step 3? We've already done step 2, and we've popped it off the stack because there's no way we have to go back to 1 for any reason. We've already explored everything to the left, okay? What do? Well, we go to the right, okay? And this is effectively the the DFS algorithm. We go to the left as much as possible. Then we do step 2 here, where we process the node and we get rid of it because there's no way we need to go back to it. We're not going to need to go back to 1. Okay, it's time. It's time for it to be processed. So then we set cur to equal to cur.right to go to the right. And now remember the whole kth smallest value thing. We're just going to return the same thing here, and let's see what we get. So it's if cur here, not if cur.left. Okay, sorry, I should have put this here. We only append it to the stack if it's a real node, obviously. Okay, you can see it's accepted. Okay, so this may be helpful to remember if you ever need to write an iterative DFS. While cur stack is going to be the condition, and it's just going to be an if-else statement. If cur, right, is pointing to an actual thing, if it's pointing to an actual node, then it's worth adding to the stack. That means that we have traversed to a node, and we may need to revisit it at some point, right? So we need to keep track of it, and that's what the stack is for. We may need to go back to 3, for example, because we still need to finish exploring its left branch. But there's also the case that we ended up in a dead end and cur is pointing to nothing. Say, for example, we're at 1 and we went to the left. In that case, we just want to figure out where we should go next. And by doing that, we can do that by doing a pop on the stack. That was for stack is for. When you don't know where to go next, when you run into a dead end, the stack will have the last node, valid node that you should be at. And you know it's going to do this because you are doing the traversal in the order that is supposed to be, right? 1 left, 2 middle, 3 right. And 3 right, by the way, you do right here at the end. After you process the node, after you're done with the current node, you go to the right, assuming that you've already done everything else on the left. Does that make sense? There's a lot of things to kind of break down there, but if you follow this logic of this code, if it will go along with how you traverse exactly. Let's go ahead and submit here. You can see the iterative solution should pass as well, which it does. So basically this problem is asking you if you know depth first search, specifically if you know how to do a in-order traversal, although it doesn't matter what kind of traversal it is. They're all depth first search, pre, post, and in are all depth first search. So you should be able to do all the others if you know how to do one. And the concept here is to do DFS. If you are not too familiar with the iterative solution, definitely just do the recursive one. There's no harm done, no foul. Just make sure you are familiar with DFS and you can code it up if you need to. It is extremely important for a lot of problems, and that has been me. Thank you.